Hello again, Matthias Fritsche speaking. And now we come to the last session of today. And this is a very interesting topic, how to measure the different single pair Ethernet installation, how to measure patch codes, how to measure installation of channels and so on. And for this very nice session, I welcome Konstantin Hüdepohl from Softing IT Networks, and he will give us a deep insight view in this topic, show up some details and all the details for this point. Thanks.
Thank you, Matthias, for the nice introduction. So very warm welcome from my side as well. I'm Konstantin Hüdepohl, working as a product manager at Softing. And my task now is to talk with you a little bit about testing of single pair Ethernet. So in the previous presentations, we have heard a lot about connectors, cables, and so on. And if you assemble all these into cabling, you need to have some measurement devices in the laboratory and in the field in order to ascertain that these cabling you have assembled is performing up to the standards that are required. So we will talk a little bit, very quick introduction about Softing. Who are we? Very short. And then we look at the IEEE applications and ISO cabling standards from the testing point of view. We then will look at measurement standards, the current measurement standards, cabling measurement standards, and also what's required for single pair Ethernet, and where we are currently at in these measurement technologies. And I'll give you a preview a little bit about prototypes and measurements that some people already did. And at the end of the presentation, I will also give you an outlook on what will come and what things that are kind of at the horizon. So very quick about Softing. Softing is a German company, management holding company. We are based outside of Munich. Founded in 1979, went public in 2000. We are about 90 million turnover, 400 employees, and we are spread all over the globe: Singapore, USA, Italy, France, Austria, Japan, India, China. So it's quite global company. We have 3 business units. Automotive, they do measurement and testing diagnostics of control units for vehicles, basically. The industrial group is doing products and technologies for industrial automation, and us as IT Networks, we do mostly handheld test devices for cabling, basically. Handheld measurement devices, we do everything from certifiers, copper fiber, qualifiers, small Ymap testers, trackers, network analyzers, and also tools for wireless testing. So that's enough of the commercial piece. So let's say that's what I want to point out, that testing actually is part of the SPE ecosystem. If you have seen this graph before in previous presentations, and the testing is here in the bottom right corner, testing in laboratories and in the field. Also important is there's a lot of SPE test standards, quite important standards we are currently working at. I'm part of the group developing these measurement standards. I'm editor in IEC, for the project editor for the single pair Ethernet measurement standards. So there's quite a lot of stuff going on at the moment. Come on. Yeah. And before we go deeper into testing, I would like to point out there's so many things you can test, and a lot of people understand very different things when they talk about testing. What I want to talk today about is cabling infrastructure tests. That are tests that ensure that cabling works to specific cabling or application standards. You can do also a lot of protocol tests. You can look up for IP devices, you can do network scans and all of these things. These are tests that are certainly very interesting, but not part of this presentation today. Applications from a testing point of view, one would be certainly the automotive industry with their needs for very light cables, multi-gigabit and so on. But that is for this presentation also not really part what I want to talk about today. I really want to talk about structured cabling for industry and offices with these quite high challenges with different lengths up to 1 kilometer, different Ethernet speeds from 10 megabit to 1 gigabit today. So this is what we really want to talk today about. From a tester point of view, really interesting applications are cabling that go to sensors and actuators, 10 megabit over 1 kilometer distance. You need these sensors and actuators. You have to ensure that they really have a reliable connection to servers and switches and so on. So these cabling needs to be tested, but also control and monitoring. Imagine sensors or actuators that sit on a robot and need quite high data transmission up to 1 gigabit. In a previous presentation, we've heard that this cabling has very high performance specifications up to 600 megahertz. So you better make sure that when you install these, that this cable really is installed properly, basically. We've seen this chart before. Why I show that again? The IEEE 802.3 applications, they are already published today. The multi-gig for vehicles is not so interesting for our purpose right now, but the other ones, the 802.3 BP, the 1000 base T1 and the BW 100 base T1 and the CG 10 base T1L. Some people only want to test cabling according to these application limits. So testers in future will also support just the application limits. They will support cabling limits, structured cabling limits, like Rainer Schmidt said before, the application independent limits, but also things like the IEEE limits. So this will be an important piece as well. One short word about Poodle. We've heard about Poodle before. What I want to point out here is, since PoE and Poodle is not compatible to each other, we will also need protocol testers in future that will do Poodle test. Will be able to run Poodle tests in the field. So that is also something I just want to point out here, because the transmission, the way Poodle is the power is transmitted over cables is very different to 4-pair and 2-pair cable. So now let's take a little bit look at connectors and those things. What is important here is we've heard about in previous talks about all the different connectors you can have for single pair cabling, which is the 1181-1 Amendment 1, for MICE 1 environment. So this is office environment basically. An LC style connector will be the preferred connector, and in harsh environment, MICE 3 environment, the -6 will be the preferred connector. What does that mean from a tester point of view? Well, we have to support test interfaces for all these different connectors. More about the connectors you can find on the single pair Ethernet partner network, of course, the web page. There's also other connectors that actually are able to transmit single pair Ethernet. Well, that's maybe wrong. That have single pair connections. Basically, that's what I should say. The Terra connector. There's the 63171-5 connector and the M8 connectors, and also terminal screws. I have seen tests where people use just on the 10 megabit over 1 kilometer application, just use terminal screws. So from a tester point of view, we have to support all these different connectors. So how do we actually connect with a tester to a link? There's two methods you can connect to a link. One is using measurement cords. That's how that would look like. So you have a tester. Basically, you have some kind of measurement cord, and you have a what we call in standards a mating interface here. And the other method is you have a direct connection on your tester. Well, both setups work. They have to comply to certain accuracy specifications, and both have advantages and disadvantages. The advantage of the upper one, with when you use measurement cords, is that it's easier to adapt to another connector. But the disadvantage, of course, is we have a measurement cord that must not influence the measurements. So somehow the tester has to remove that cord from the measurement. That is, from a mathematical point of view, quite a bit of a challenge, but doable. So some testers on the market do this. And the other method is, of course, you can connect directly to the tester. The advantage here is it's much easier for the tester because there's no measurement cord that needs to be removed. The disadvantage is, well, you have to develop lots of different style test adapters for it. So you see both is, I would say, deliver equally good or bad results, but both have advantages and disadvantages. It's up to the user to decide which one to use. If you go back to the cabling standards, Rainer Schmidt mentioned that before already, the TR 11806-9906. This is an available standard you can already use. Well, it's not a standard, actually, it's a technical report. It's slightly less than a standard. The technical report basically is available now. We could implement that in a tester right now. That basically supports these applications. So the ones that are really interesting for structured cabling. The multi-gig application is not supported, and also the 10-base T1S application, which is a point-to-multipoint application. So actually a bus structure actually is not really supported in that 9906. We'll come to point-to-multipoint a little bit later in the presentation. If you look at generic cabling, we have seen that also in the previous presentation. Important to mention here is that actually the testers will have to support all these generic cabling classes. Like some people already may be familiar to in the audience, the class E or class EA or class F and so on, cabling limits that are available today for normal office use. You will have similar things here for in test devices for single pair Ethernet cabling. What's also interesting is the ISO IEC is an international standard. There are similar activities in TIA, and there also will be a comparable project in Senelec for the EN standards. So you see that many people actually work on these activities at the moment. Interesting also is that these generic cabling classes foresee a number of different connectors in the cabling. So, for example, the application, the independent standard T1A-1000 allows 10 connectors. From a testing point of view, that's why I bring that up here again, is from a testing point of view, you always have to test the complete assembly, the whole thing, basically. Like here in this example, the T1A400 channel. You cannot take one segment of the cable, test that, take the next segment, test that, take the next segment, test that, and then join everything together and say, well, this will work. That's not how these tests work. The definition says you always have to test the whole assembly. There's also another little catch here. Look at this assembly where this example here, somebody has made an assembly of a 500-meter piece of T1A1000, sorry, another 400 meters of T1A 1000, another 10 meters of T1A 1000. You could imagine this goes through different buildings or something like that. And actually the last pieces are T1B cables, maybe because they are just thinner and easier to connect, or something just was just lying around somewhere. So how do you test that? Can I test that to T1B limits or T1A 1000 limits? In the cabling tests, important thing is that always the lowest performing piece is the, from an RF measurement point of view, is the limiting thing. So the T1A 1000 is a 0.1 to 20 megahertz link. And this one is a 0.1 to 600 megahertz link. So from an RF point of view, this is the lower performing thing here, the T1A. So actually what you need to do is you need to test this particular example to T1A 1000 as an example. So just to be cautious with that. Same, by the way, happens also in office cabling. If, for example, if you have a wonderful category 6A permanent link installed in your building and you attach Cat5e patch cords to it, it's not a class EA link anymore, it's a class D link. Same thing here again. All right, so this was about cabling and how this will be implemented in testers. And now let's look at measurement standards, because cabling standards and measurement standards are separate things, at least in ISO. In TIA, it's mixed with each other, but in ISO IC, it's separate things. So there's an ISO IC working group, TC46 working group 9, that actually defines how to measure those installed links and channels in the laboratory as well as in the field. There's one standard called ISO IC 61935-1 that is around for a long time already, now in its, I believe, 5th revision, that defines how to measure things like crosstalk, return loss, insertion loss, all these parameters in the laboratory as well as in the field. But this standard is only applicable to 4-pair cabling, so it's not really applicable for 1-pair cabling. The -2 standard defines how to measure patch cables. So if you buy a category 6A patch cable, for example, this standard tells you how to measure that. And for industrial purposes, there's this end-to-end links. They are defined in 14763-4. So they, as I said, they define everything, every measurement parameter. So the direct current parameters like resistance, delay, and so on, and the RF parameters like next, return loss, insertion loss, ACRN, ACRF, and so on and so forth. Both, as I said, in the field and laboratory. And they define accuracy levels. So how accurate do I have to measure this? And in order to have accuracy levels, the accuracy definitions, you also need error models. So what are the contributed errors of connectors, of cables, of your measurement setup, and so on? That's all defined in the -1. So there's a new IC project now coming up for measurements on single pair cabling. It's in the same series, so it's going to be ISO IC 64935-4. We've just, the working group 9 has just released the new work item proposal as a working draft for measurements on single pair Ethernet. This work item proposal is now submitted to the upper group TC46 for approval. And if everything goes well, and I believe it will, TC46 will, I believe, next week accept that new working item proposal and will launch that as a new project. Standards are not really exactly very fast, so my estimate is that this publication will take about 2 years. And the colleagues at TIA, so the American colleagues, they have a similar activity. They will be probably a little bit faster, and there's no activity in Senegal. I mentioned that before. I happen to be the project editor of that new working draft, so I'm quite excited to actually be able to contribute to that. If you compare 4 pairs and single pair measurements to each other, you can look at this little table here. This column here shows 2 and 4 pairs, and the right column shows 1 pair measurements. So of course you have to do a wire map. Wire map on 1 pair is not very exciting, but at least you have to make sure that the 2 conductors and optional shield are connected properly. You have DC loop resistance. Loop resistance, you measure in a loop from one end of the cable the resistance of conductors. There's a relatively new parameter, DC resistance unbalance. So that in a nutshell, that measures single wire resistance. That became important for 2 and 4 pair cabling, mostly for 4 pair cabling, for 4 pair power over Ethernet applications that go up to 90 watts, because cables in that high power range can become substantially warmed. So the loop resistance measurement wasn't good enough anymore. So you need to take care about single wire resistance. On a 1 pair cabling, it is more difficult because you cannot, if you have an unshielded cable that's 1 kilometer long, for example, or like it just doesn't end at the same location, you can't do a single wire measurement anymore. So there are discussions if that parameter actually is doable in the field, and how should we measure that in the field. Of course, you need to measure insertion loss. Insertion loss is just, you send signal in at one end and it gets attenuated to the other end. Return loss is a very important parameter for single pair cable as well. Return loss is basically you send signals in from one side and you get reflections back. So this is an important parameter. Then you have all the crosstalk parameters. Well, that's easy because in single pair, there is no other pairs that could cause crosstalk. So it's not an issue. But wait for that, we'll come to crosstalk a little bit later. So then there's alien crosstalk. Alien crosstalk is the crosstalk between cables and cable bundles. We come to that in a later slide. And there's things that try to measure the electromagnetic immunity of cables. Transfer conversion loss, TCL, and ELT-CTL, they basically works good on unshielded cable, but there's still questions and limit discussions and so on shielded cables. Coupling attenuation and LCL and so on, these are more laboratory measurements that cannot be really measured in the field. I'll show you later on pictures of this measurement. So there you see there are still some question marks here, which we need to answer mainly in the new edition of this dashboard standard. There are other topics we need to cover in the new measurement standard. One is the frequency range. The classical 61935-1 for 4 pairs covers 1 megahertz to 2000 megahertz. Single pair actually needs 0.1 to 600 megahertz, and in future 1250 megahertz. So we have to cover a new frequency range in that new standard. We earlier talked about the accuracy levels. The -1 knows 6 accuracy levels. Most of them do not match for single pair. So we have to create new accuracy levels. We have to do the homework to check if all the parameters work in these new frequency ranges. It's a bit of homework we need to do there. We have to confirm error models. We most likely will not need new error models, but we have to confirm that the old error models still work. So there's a lot of homework we need to do for the dashboard standard. We talked about alien crosstalk earlier. So alien crosstalk basically is you have this cable bundle here, like you see here on the right side of the screen. This red cable here is the so-called disturbed channel. And around the disturbed channel, you have a lot of disturbers, so cables that send crosstalk basically into the red cable. So we have to define strategies how to measure that in the field. That's basically what needs to be done. And now we come back to crosstalk between pairs in one cable, because there's one interesting application called cable sharing, where we run 4 one-pair applications in one 4-pair cable, or maybe a part of the cabling is a 4-pair cable, and then you have split outs to 1-pair cabling. So basically, we have to define measurement procedures, how to measure these situations in cable sharing. So actually, somehow Next is back again. If you look at that now from a status point of view, we have to define the frequency ranges. We have to define accuracy levels and error models and reference models. Reference models is like, so this is the reference model for a channel. So this is the reference setup. How do you measure that, basically? That is relatively simple. We cannot adapt a lot of that from the 4-pair measurement standard. Then we have things like alien crosstalk in bundles, in multi-pair cables, and also measurements of patch cords. That is a bit more complex and needs to be defined. And really openness at the moment is how to measure point to multipoint. A few words about mice. We have heard about mice in earlier presentations. In mice 1 applications, basically they don't need any special field measurements in regards of the immunity for external electromagnetic influences. It's okay if you measure that in the laboratory with coupling attenuation measurements, but you don't have to measure that in the field. But in the industry, mice 2 and mice 3, so electromagnetic harsh environments often prevail. Power lines, welding machines, powerful electric motors, all kinds of things that send out a lot of electromagnetic interferences. So cabling has to be very robust against those interferences, and we have to find test methods how to test that. So one thing is, if for unshielded cables, you can use the TCL measurement. For shielded cables, there's still discussions, and it's not clear how that will go. And in the laboratory, you can use coupling attenuation measurements. On the bottom of the screen here, you see a setup for that. So it's a little bit small, but I hope you can see that. There's a spectrum analyzer here and a 3-meter measurement tube in which a cable sample is run here. So imagine that is not really something you want to run through a production site, right? So we have to find other methods, basically. Some examples, prototype examples. One is from our colleagues from Fluke Networks. That's the DSX5000 and the DSX8000. With measurement adapters, basically. And from us, from Softing, the WireXpert 500 and 4500 with measurement cables, basically. And I have here 2 different examples with the bottom one is a setup we have done for first tests on alien crosstalk. That's why it has 4 ports here. You can basically measure 3 disturbers against 1 disturbed cable, basically. And for regular measurements on just a 1 cabling, a 1-port adapter, basically. So these both are in prototype stage, and I wanted to show not just ours, but to show other manufacturers as well here, to show that this is something where actually more people work at. So how do measurements look like? Well, if you run this would be a T1B measurement, so that actually goes up to 600 megahertz. The Ymap you see here is not so super interesting. It's only 1 pair and a shield, and you get some overview on insertion loss and return loss. And if you look a little bit closer, you get resistance values as well, and the measurement. This is insertion loss measurement. In our tests we run currently in our laboratories, we always run up to actually 2 gigahertz, just to the fun of it. The limit only goes up to 600 megahertz, but the measurement we always do run on a higher scale to see the trend, where's the performance going to, because we always keep in mind that in future there's also this 1250 megahertz thing coming up at some point. This is return loss measurement. So also there, the measurement, the limit is only up to 600 megahertz here, and we've measured the whole range basically. And if you look at the printed report, of course, the testers would then also give printed report with, the printed report always contains a section with the DC values basically, and then a section for this would be insertion loss and the return loss. So for the RF parameters, the worst case values, as well as the plots basically. So this measurement basically is a measurement that has a pass. So, but what would you do if you have a fail? Because if you look back at this measurement here, these measurements are in a frequency domain. So they don't really tell you something where a fault happens. The testers will tell you the fault is more detected from the near end or it's detected from the far end, but they don't tell you where exactly the fault is. So in that case, you need to have some more troubleshooting. And I have just one example here. One is also, again, with the courtesy of our colleagues from Fluke here, an example. You have a 5 meter good segment and a 2 meter bad segment. So the cable here is poor quality cable. And what you have here is a HTDR, high definition time domain reflectometer, where you basically where the tester basically converts everything into a length dependent reading here. So this shows here that this here is the first segment you see here. There's very little readings, and then you see a lot of signals going on here. That would be the 2 meter that are bad. So those, just one example for a bad cable segment. Another example here from our testers, from a wire expert tester, would be you have a 5 meter bad good segment again, and also 2 meter good segment here, but the connection here is bad. Either it's poorly terminated, or the connector is not rated for that performance, or whatever. It could be anything. What you see here is again a small peak for the first connector, and here you see a small peak for the last connector, and you see this huge peak here for the bad connection, I should say. So with those additional functions, you can do a lot of troubleshooting in the field if you have a failed cable, and basically can find out where along the cabling channel you have problems. I should also say that these both tests here have no limit lines, because the cabling standards basically focus on the RF parameters. They don't really offer limit lines here. So this is basically just a how you say, subjective view if a connector is worse or better than another one. But it's a very good measure in the field, and it will show you if where faults are. Well, so this is about troubleshooting. Now let's give you a little bit of an outlook. What also is, from our point of view, will be interesting. If you go back to the IEEE standards, when you talk about that with my colleagues in the business unit industrial automation, they say, well, 1000 megabit is nice, but in future we will need more. So also from a testing point of view, we will have to foresee that these standards will evolve at some point. Short distance, is maybe they would like to see longer distances. So also from a testing point of view, we have to foresee that actually this is not the end. We will have to test longer segments with higher speeds. Again, here short distance, and 1500 meters is the minimum a lot of people want to see. So you can see that the things we are working right now on, cabling standards that we are working right now on, is a very good start, but you can see that there's also already a roadmap where things for the future will happen. What also is open, I've talked before, point to multipoint applications, point to multipoint. So we are actually back at bus structures for now, bus structure for Ethernet. So how would you test that? If you just connect your tester to the very ends of that bus, you have a lot of opens here, right? And these opens, they will give you a lot of reflections back. So that test would certainly fail. So this is not an option. This will not work. What we could also do is we could terminate all the ends and just test from the extremes. That is one scenario. Another scenario would be you could start testing from one side, then move your tester to the next location, and so on and so forth, and jump around all the locations and somehow do a summary measurement evaluation of that. So these definitions on how to test point to multipoint, they are still open. The colleagues at TIA are a little bit more advanced than in that question. They have already discussed that a little bit more than us at IEC, but watch this space. There will be also some definitions coming up for point to multipoint testing. Another alternative here might actually be that we don't use the classical RF testers anymore for that, but use protocol testers. You could say, okay, I'll just go around and test if I get my 100 megabit or gigabit or whatever speed at every point of that multipoint location test, multipoint link. Could be an alternative for that. So it's going to be an interesting discussion, I think. Well, that brings me, I think, to the end of my presentation already. I don't know how I'm working on time. I'm a little bit fast, but that's okay. Matthias, do we have questions?
Yes, yeah.
Good.
We have some questions, and some of our participants asking some questions regarding troubleshooting. So,
Okay.
for example, if you have a patch code with two connectors and one of these connections is not assembled in the right way, how they can identify which one is the bad one? Is it possible with the measurements we have today?
Well, there's two scenarios. If you only test that cord, right? If it's if you do that like a patch cord test, the tester gives you an information if if the error is found at the near end of the test or at the far end of the test. That is fairly easy because it will tell you, for example, crosstalk. Well, there's no crosstalk. Sorry, return loss fails on the far end of the cable. The more complex situation is if I go back to my troubleshooting example here. If you have something like that here, if the patch cord is part of the assembly, the tester, if the patch cord is somewhere at the end of the assembly, the tester will still tell you, well, the patch cord at the near end. Oh, sorry, the test failed at the near end, so it's most likely the patch cord on the near end. But then I would really recommend to use features like the TDR or the time domain return loss to actually look at the length display basically and find out from there which part of this, which segment of the test is not good.
Okay, interesting. So thanks from my side, and also I think from all the participants for this very interesting information. It was also one of the very interesting sessions from my side, because I'm also not so familiar with high frequency testing. I have personally one question. So we have also a tester from you, and in the future, if something will change in the specification how to test and new standards come up, of course, this is possible with the software and the firmware update, that we get this new parameters and everything in our testers to have it updated.
Well, let's put it that way. In the testers you buy today, they can be upgraded within their original specifications. So, for example, if the specs for testing Class EA cabling, if something changes there, the tester can be updated for that. For single pair measurements specifically, you have seen that there's quite a few open questions still. And at the current stage, because we are really at the beginning of the new measurement standard, I would not really guarantee that yet, because there's still quite a few open questions here. One is, for example, the frequency ranges.
Yeah.
The new some of the cabling starts at 0.1 megahertz. On the other hand, it's not yet really clear if we have to really start giving a pass-fail on this low frequency. So, for example, if you would just have to start with a pass-fail at 4 megahertz, for example, you could use the current tester still. So there's a lot of open questions still on that.
Yeah. Okay, thanks for all these details regarding the measurement and all this, very interesting things where we have also work to do for the future. But still, we have already the first test equipment available, and we can start to test also cables we deliver to customers and so on.
Absolutely.
So thanks.
Yeah. I mean, we use the setups I showed you. We use that already with some beta sites, basically, to gain more experience also, and help first beta sites. So it's an interesting field and a very interesting topic to work on.
Yeah, we are also producing the first cables and test it according to the specification and details you show up today. Yeah. Mm-hmm. So thanks a lot. And this is,
thank you.
Yeah, this is last sessions for today, and I will not miss it to give you some hint also for tomorrow. We continue tomorrow morning at 9:30, and the morning sessions are all related to use cases, and not only use cases where we show up some slides and say it could be possible and so on. It's really use cases where some of our members and other companies working on and starting launching products. So it will be very interesting. You have a new link for this session. So we are happy to see you again tomorrow morning, and enjoy the evening. Have a nice, relaxing time, and see you tomorrow morning again for the next sessions. Thanks for all who joined this very interesting day, and goodbye from my side, and also I think from all the other presenters, and including Konstantin for today.
Thank you very
much. Nice greetings to Munich.
Thank you. Greetings back to Rade. Bye-bye.
Bye-bye.